Welcome to the deep dive. We are so glad you are here with us today. I was thinking earlier about how we look at engineering in the physical world.
Oh, right. Like physical infrastructure.
Yeah, exactly. Like, if you are a civil engineer building a suspension bridge, or, I don't know, an architect designing a skyscraper, there is this underlying expectation of absolute mathematical precision.
Right, there has to be.
You do the calculations for load bearing, you measure the tensile strength of the steel, you account for wind shear, and if the math works, the bridge stands. It's binary.
Absolutely. You don't just build a bridge, drive 1,000 trucks over to see if it falls down, and then shrug and say, well, I guess it's good enough.
Exactly, because in physical engineering, the mechanics are visible,
Yeah,
right?
yeah.
And the governing laws, like physics, thermodynamics, gravity,
They're universally agreed upon.
right, and they are rigorously applied before a single piece of metal is ever forged. But then, as someone who spends a lot of time looking at the digital world, you step into the realm of software development.
Oh, boy. Yeah.
And specifically web infrastructure, the actual plumbing of the internet itself. And suddenly that rigorous mathematical certainty just kind of vanishes. The blueprint is gone.
It really is. It's a completely different mindset.
We are looking at a landscape that is, well, honestly, a bit murky. We build these massive global web servers that handle billions of transactions, and we don't actually know their absolute limits. We just stress test them.
It is the absolute definition of empirical guesswork.
Right.
I mean, in the software industry, the standard operating procedure for scaling a server is to build it, put it on a really powerful machine, and then just blast it with simulated traffic.
Let's throw everything at it.
Exactly. We throw requests at it until it buckles under the pressure and crashes. And if it survives long enough to handle our anticipated Black Friday traffic, we call it optimized.
Like it's some sort of mysterious beast that we're just trying to keep fed and happy and, upright.
That's a great way to put it, yes.
Which brings us to our mission for today's deep dive. We have a fascinating stack of source material in front of us today, detailing a completely new web server called x-gnosis.
And x-gnosis does not play by those good enough rules.
No, it doesn't. It doesn't rely on that empirical guesswork at all. In fact, it claims to be something that sounds almost like science fiction to anyone who has ever written a line of code.
It claims to be the first provably optimal web server.
Provably optimal.
Yeah, and that is a phrase that should stop any software engineer, or really anyone who relies on the internet, right in their tracks.
Because we aren't talking about something that is just marketed as like highly optimized or blazing fast.
Right, those are just marketing terms thrown around every single day. We're talking about mathematical, provable optimality.
So our goal today is to figure out exactly what that means, how it actually works under the hood, and why you, as the listener, should care about this.
Because it really is a massive shift.
It is, because if this material is accurate, we're going to explore how x-gnosis replaces the standard trial and error benchmarks of the tech industry with literal mathematical theorems.
And we're going to dig into how it magically manages to run legacy code from almost any web framework you can think of.
Which is wild.
Yeah.
And ultimately, we'll look at what the zero-deficit mindset means for the future of the internet's fundamental infrastructure.
What we are really analyzing today is a paradigm shift. We are looking at the transition from software as an empirical guess, where we observe its behavior in the wild and patch it when it breaks.
To software as a mathematical certainty.
Exactly. It is, quite literally, the transition from alchemy to chemistry in the realm of server architecture.
Okay, let's start right at the foundation.
Yeah.
Because to understand x-gnosis, we have to really grapple with this core claim about optimality.
Right, the mathematical proofs.
Yeah. When someone says a web server's speed is a mathematical certainty, I struggle to picture what that actually means. Usually, if a server is incredibly fast, it's because some brilliant engineer stayed up for a week straight, drinking energy drinks, finding clever shortcuts in the code, right?
Well, yeah, that's the traditional hacker ethos for sure, finding a clever workaround to shave a few milliseconds off a process.
Right.
But x-gnosis approaches the problem from the complete opposite direction. It's throughput bound. The absolute maximum amount of data it can process is not a benchmark. It is a mathematical theorem.
A theorem.
Yes, they call it the THM Server Optimality Composite Theorem.
Okay, THM obviously stands for theorem, but the sources call this a composite of 14 mechanized theorems.
Mechanized, yes.
I have to be honest, I hear mechanized theorem and my brain just imagines a robot doing algebra. What does that actually mean in the context of building a web server?
It means that the proofs underlying the server's logic have been independently verified by a computer, rather than just reviewed by a human being on a whiteboard.
Okay, because humans make mistakes.
Exactly. Human beings make logical leaps. We assume things. A computer does not. The sources specifically state these theorems are model-checked in TLA Plus and proven in Lean 4.
Okay, let's unpack this. TLA plus, let's break that down first. What is that?
So TLA Plus stands for Temporal Logic of Actions. It was invented by Leslie Lamport, who is a legendary computer scientist.
Okay.
Think of it as a blueprinting language for highly complex systems. When you have a system with lots of moving parts, like a web server handling thousands of concurrent users,
Huh.
it is just impossible for a human brain to anticipate every possible state that system could be in.
There are just too many variables.
Right, too many moving pieces. So TLA Plus allows an engineer to describe the system mathematically, and then the software checks every single possible state to ensure that it never reaches a fatal error.
Like a deadlock or something.
Exactly, like a deadlock where two processes are stuck waiting for each other forever and the whole server crashes.
Wait, so typical web servers are like tuning a race car on a track to see how fast it goes, but x-gnosis is like a physicist proving the absolute mathematical limit of thermodynamics for an engine before it's even built.
That is a brilliant way to put it, yes.
Yeah.
You are mathematically proving that you will never accidentally put your own king in check, to use a chess analogy.
Oh, I like that.
And then, combined with TLA Plus, they use Lean 4. Lean 4 is both a theorem prover and a programming language.
Okay.
You write mathematical proofs in it, and the compiler strictly checks them. And the key phrase the creators use in the documentation to describe their Lean 4 proofs is that they are sorry-free.
Sorry-free. I love that phrase, but I assume it doesn't mean the developers are just refusing to apologize for their code.
No, not quite.
What is a sorry-free proof?
Well, in Lean 4, when a mathematician or a programmer is writing a really complex proof, they might hit a step that is incredibly tedious to prove.
Or maybe they just can't figure it out, right then?
Exactly. The language actually allows you to type the word sorry as a placeholder.
Wait, really? It just lets you skip it.
Yeah. It effectively tells the compiler, look, just trust me on this specific logical leap, assume it's true, and let me keep writing the rest of the proof. I'll come back and fix the sorry later.
Ah, so it's basically a structural IOU.
That's exactly what it is, an IOU.
Uh-huh.
But a sorry-free proof means there are no IOUs.
No skip steps.
None at all. There are absolutely no logical gaps. Every single deduction, from the base axioms to the final architectural conclusion, has been rigorously mathematically verified by the machine.
Wow.
It is logically watertight. There are no leaps of faith.
Okay, so the math is sound, it's airtight. But what does the math actually guarantee? We have this watertight, sorry-free proof. But what does it dictate about how the web server behaves?
It guarantees two foundational principles. The first is called critical path makespan.
Makespan, like the span of time it takes to make something.
Precisely. In scheduling theory, makespan is the total time required to finish a complete set of tasks. Now, any web request can be mapped out as a sequence of required tasks. First, you receive the connection, then you parse the headers, then you route the request, fetch the data, and send it back.
Right, a step-by-step process.
The math proves that no admissible schedule operating on that same directed acyclic graph of tasks can serve the request faster.
Yeah, wait, I need to pause you there. Directed acyclic graph. Let's make sure we aren't leaving anyone behind.
Fair enough. A directed acyclic graph, or a DAG, is basically a flow chart that only moves in one direction.
Okay.
Directed means the arrows have a specific direction. Acyclic means there are no cycles. You can never follow the arrows and end up back where you started.
So you can't loop back around.
Right. A web request is essentially a DAG. You can't fetch the data before you parse the request, for example. There is a strict one-way order of operations.
Okay, so it's essentially an assembly line.
Yes, exactly like an assembly line.
Yeah.
And the critical path makespan theorem proves mathematically that given that specific assembly line, it is physically impossible to process the request any quicker. Period. They have hit the absolute mathematical floor of latency.
That is wild. It literally can't go lower. So what is the second guarantee?
The second is Pareto optimal resource usage.
Pareto optimal.
Right. This means that no other schedule or server architecture can beat x-gnosis on both speed and the number of workers, meaning CPU threads, that it uses.
Let's explore that Pareto frontier concept a bit more.
Sure. You might be able to design a theoretical server system that uses fewer CPU resources than x-gnosis.
Okay.
But the math proves that system will be slower. Conversely, you might hypothetically design a system that is equally as fast, though not faster, because of the first rule.
Right, the makespan rule.
Exactly. But the math proves it will require more CPU resources.
Yeah.
X-gnosis sits exactly on the Pareto frontier. It has found the perfect, unimprovable balance between blazing speed and minimal resource consumption.
And the sources provide empirical evidence to back up this math, right? What kind of throughput are we actually talking about in the real world?
The benchmark in the documentation is just staggering. 7.6 million requests per second.
7.6 million
Yes.
in 1 single second.
In 1 second. But the crucial context, the thing that makes this truly revolutionary, is that this benchmark was achieved on a single-thread pipeline.
Wait, a single CPU thread?
One single core doing the work.
That's insane.
To give you some industry context, the sources point out that this single-thread result beats the #1 spot on the famous Tech and Power benchmarks.
Oh, the Tech and Power benchmarks are huge.
Yeah, they are the gold standard. The previous champion was a server called Mini TP, but that server required 56 CPU cores to hit its top-tier throughput.
So x-gnosis is beating a 56-core champion using just a single thread.
Exactly.
Okay, I have to stop and wrap my head around this because this completely flips the script on how software is built. Usually, if a team wants to beat the Tech and Power benchmark, they build a server, they run the test, they see it only hits, say, 1 million requests.
Right, they see the bottleneck.
Then they use a profiling tool to find out where it's choking. They realize, oh, the logging function is too slow. They rewrite the logging function, run the test again, and now they hit 1.5 million. They iterate. They guess and check.
That is the empirical tuning-based approach that 99.9% of the industry uses.
But x-gnosis didn't do that at all. It sounds like they sat down, proved the absolute mathematical limit of what a computer processor could theoretically do with a single stream of network data, and then just built the server to match the math.
That is exactly what happened. What's fascinating here is that the creators explicitly state the 7.6 million requests per second isn't a highly tuned lab trick.
It's not just a clever hack.
No, it's not the result of months of iterative hacking. It is simply the physical realization of that mathematical boundary in the real world. The architecture of the server was derived from the math, not the other way around.
The documentation mentions a phrase regarding the speedup. It says the speedup is definitional in lean.
Definitional, yes.
Meaning it's not a rough estimate. It is an exact, calculated multiplier based on the principles of what they call zero-deficit routing. How does zero-deficit work in this context?
Well, to understand zero deficit, you really have to understand queuing theory.
Okay.
In most traditional servers, as web traffic increases, requests start forming queues. Think about a supermarket.
Oh, like checking out.
Yeah. If one cashier has an issue with a barcode, the line behind them stops moving. That delay is a deficit.
Right, everyone has to just stand there.
Exactly. In a web server, if a CPU thread gets stuck waiting for a slow database query to return, the requests queued up behind it are blocked.
They're just stuck in the supermarket line.
Right. X-gnosis uses mathematical topology to ensure what they term lossless information transport. Zero deficit at every layer means there is absolutely no cross-path blocking.
So nobody gets stuck behind the broken barcode.
Exactly. If one request is waiting on a slow database, it physically cannot block another request that just needs, say, a fast static image.
Okay, that sounds beautiful in theory, but I want to know how that works in practice. How do you physically prevent those traffic jams inside the CPU?
You have to rethink the routing.
Right, because since the mathematics dictate that there is a perfect way to handle a request, how does x-gnosis actually mechanically route a user's web traffic to achieve this zero-deficit reality?
That requires us to dive into its scheduling layers. X-gnosis relies on a specific structural design called the Eon Flow Protocol topology.
The Eon Flow Protocol.
Yes. Every single request that enters the server flows through 5 distinct stages: accept, parse, route, resolve, and respond.
And looking at a breakdown, they map these stages to specific operational verbs, right? Accept is a for, parse and route are process, resolve is erase, and respond is a fold.
Yes, that's the sequence.
I want to zero in on that resolve layer because the concept of erase seems entirely counterintuitive to how I understand traditional computing.
The resolve layer is arguably where x-gnosis radically differentiates itself from anything else on the market. Let's think about how a traditional web server handles a request for a static file, like a company logo image.
Okay, pretty standard request.
Normally, the server executes a sequential checklist. First, it looks in the fast memory cache. If the logo isn't there, it might check a memory-mapped file structure.
Right.
If it still can't find it, it finally goes all the way down to the physical hard disk to read the file, which is a comparatively very slow process.
Which makes total logical sense. It's like looking for your car keys. You check your pocket first because it's fast. You only tear apart the couch cushions if they aren't in your pocket. Why would you tear apart the couch immediately?
It makes intuitive sense to us as humans, yes. But sequentially checking takes time. Even checking the fast cache takes a few microseconds.
Every check adds up.
Right. X-gnosis throws out the sequential checklist entirely. Instead, it initiates a simultaneous three-way race.
A race, like all at the same time.
Exactly. The very microsecond a request comes in, the server forks the request and fires off three completely separate computational tasks at the exact same time.
Simultaneously.
Um,
Okay, what are the three tasks?
So one thread immediately checks the cache, which operates in microseconds.
Right, the fastest one.
Second thread immediately checks mmap, the memory mapped access, which operates in tens of microseconds. And the third thread goes straight to the hard disk, which operates in milliseconds.
Wow.
All three start sprinting toward the goal at the exact same moment.
Okay, but only one of them is going to find it first.
Exactly. And the moment the fastest thread, let's say the cache finds the file and succeeds, it is declared the winner. And instantaneously, the other two threads, the ones checking mmap and the disk, are what x-gnosis calls vented.
Vented, meaning cancel.
Aggressively and immediately canceled, yes.
Let me try to visualize this. It's like you're incredibly hungry, so you order the exact same meal from 3 different restaurants on 3 different delivery apps.
Okay, interesting analogy.
You have one coming by bicycle from a place next door, one coming in a car from across town, and one being flown in by a drone. The absolute second the guy on the bicycle hands you the food, the drone and the car simply vaporize into thin air.
That is a highly aggressive way to acquire lunch,
Yeah.
but computationally, yes, that is exactly the logic at play.
But here is where my skepticism kicks in. I hear that and I think, well, that's just waste. Doesn't that waste precious compute resources? You are spinning up 3 distinct CPU tasks when you know you only need one.
It seems like it would be yes.
If the cache is going to hit almost instantly anyway, why even bother waking up the disk drive? Isn't that the opposite of Pareto optimal resource usage?
It's a very natural question, but this is where the genius of the architecture lies. We have to go back to the zero-deficit mathematics.
Okay, the math again?
Why does x-gnosis do this? In older legacy systems, if a server had a slow task running, say, a massive disk read for a different user, the internal scheduler might get bogged down.
It gets overwhelmed trying to manage everything.
It could artificially serialize requests. So you might have a situation where your request for that logo could be served instantly from the hot cache, but the system forces you to wait in line behind someone else's slow disk read just to figure out what to do with you.
Ah, I see. The management overhead of deciding who goes where actually becomes the bottleneck itself.
Precisely. By initiating a race, x-gnosis bypasses the decision-making bottleneck entirely.
That's brilliant.
But to your point about wasted resources, it only works because of how efficient the venting process is.
The vaporization.
Right. In a traditional operating system, canceling a thread is messy. It requires overhead, cleanup, and context switching. Because x-gnosis uses mathematical topology for lossless information transport, it can drop those unneeded threads instantly at the CPU level with practically zero penalty.
So it doesn't take time to clean up the mess.
No, it doesn't wait around to clean up memory. It drops the loser threads, freeing up the CPU cycles for the next user's request before a legacy server would have even finished deciding which queue to put the first request into.
That is fascinating. So the speed gained by not making a decision drastically outweighs the microscopic cost of firing the starting pistol for 3 threads.
Exactly. But the efficiency doesn't stop there. The sources detail another mechanism in the resolve layer called middle-out projection caching.
Middle-out projection caching. Okay, walk me through that.
Imagine you have a highly anticipated news article dropping on a website or a flash sale on an e-commerce site. 100 different users click the link and request that exact same highly customized dynamic page at the exact same millisecond.
A huge spike in traffic.
In a traditional server architecture, the server receives 100 requests, and it obediently starts building that dynamic page 100 individual times. It queries the database 100 times, renders the HTML 100 times.
Which is a massive cascading waste of database power and CPU energy.
Yes, but x-gnosis is flow-aware. With middle-out projection caching, the server recognizes the underlying signatures of these in-flight requests. It sees that 100 people are asking for the exact same complex computation simultaneously.
Oh, I see where this is going.
Instead of duplicating the work, It coalesces them.
Coalesces them, like grouping them together.
Exactly. It effectively says to the 99 concurrent request, hold on, I am already building this exact projection for the first user. Don't start a new process. Just wait a microsecond, attach yourself to this process, and when the result is finished, I will copy it to all of you simultaneously.
Oh, wow. It reminds me of a brilliant short order cook at a diner.
How so?
If 5 different tables order a mushroom omelet at the exact same time, a bad cook would make 5 separate omelets one after another in 5 pans. A great cook throws all the eggs and mushrooms onto one massive flat-top grill, cooks it all at once, and slices it onto 5 plates.
That is a perfect analogy. Concurrent requests join a single specialization pass instead of performing redundant work. And because it's rooted in the mathematical topology we discussed, it handles this grouping dynamically on the fly with zero risk of sending the wrong data to the wrong user.
Okay, this is all incredibly elegant. We have this mathematically derived engine that races internal processes and groups identical tasks flawlessly. But as someone who looks at industry adoption, I have a massive glaring concern.
What's that?
A mathematically perfect engine is a great scientific achievement, but it is entirely useless if it doesn't fit into the cars that people already own and drive.
Ah, the legacy problem.
Right. Most of the internet runs on deeply entrenched legacy technology. Companies have configuration files that were written a decade ago. How on earth does x-gnosis adapt to the messy legacy reality of the internet we actually use today?
You've hit on what might be the most practical and arguably brilliant engineering decision in the entire x-gnosis project. The creators understood that if they required every sysadmin, every DevOps engineer at every company in the world to rewrite their entire infrastructure from scratch to use this new math, the adoption rate would be zero.
You would just be an academic paper gathering dust.
Exactly. So they built a bilingual bridge.
Mm.
X-gnosis natively parses standard nginx.const syntax.
Wait. Nginx is arguably the most popular, widely used web server software in the world. It acts as the reverse proxy for millions of sites. You're saying that an engineer can take their existing legacy Nginx configuration file with all of their bespoke listen directives, their complex server name routing rules, their specific gzip compression settings.
Just hand it to X-gnosis.
Yes.
You don't change a line to your config file.
That's incredible.
But here is the critical distinction. X-gnosis does not run Nginx code. It doesn't emulate Nginx. It reads the legacy text file, parses the intent of your instructions, and then it literally compiles those legacy directives into its own .jek mathematical topology programs.
So it looks at my old school instructions and translates them, mapping them directly onto its high-performance engine. It acts as a complete drop-in replacement.
Exactly. It lowers the barrier to entry to absolute zero. But the bilingual nature of X-gnosis goes much deeper than just reading configuration files. The documentation explains that the server actively speaks a dual protocol on the network layer.
Okay, so it speaks 2 languages. What are the 2 protocols?
The first one is standard HTTP 1.1. This is the universal language of the web. It's what standard web browsers like Google Chrome, Safari, Firefox speak. If a regular browser connects to X-gnosis, the server politely speaks normal, standard HTTP.
Like a tourist speaking the local language.
Right. But the second protocol is where the real revolution lies. It is a proprietary protocol called Eon Flow, designed specifically for what the documentation calls flow-aware clients.
I was looking at the numbers on this Aeon Flow protocol in the sources, and the claims are staggering. It says Aeon Flow uses 10-byte self-describing frames, and it has 0 per request headers. The document literally states the stream ID is the request. Can you explain why that is such a big deal?
Well, to appreciate this, you really have to understand how bloated and inefficient the modern HTTP web has become. Think about what happens when you request a single file, let's say a tiny CSS-style sheet, using standard HTTP. Your browser doesn't just ask for the file, it sends a massive block of text headers.
Right, all that extra data.
It sends your user agent string, which details your exact operating system and browser version. It sends your language preferences. It sends a massive block of tracking cookies. It sends all of this metadata with every single tiny request.
It's like sending a 10-page biography of yourself every time you ask someone for the time.
Exactly. And when a modern website loads, it's often requesting 50, 60, or 100 different tiny files simultaneously. Sending that massive block of headers 100 times completely clogs the network.
Just a huge waste of bandwidth.
Eon Flow completely strips all of that away. Because Eon Flow is explicitly designed around the fork graceful topology we just discussed, it multiplexes streams effortlessly. The stream ID intrinsically tells the server everything it needs to know about the context of the request.
The server just knows.
Yes, the overhead is practically non-existent.
The source material provides a head-to-head comparison to illustrate this, and the math here is wild. They tested a microfrontend site. For listeners who don't know, a microfrontend is a web design pattern where a single page is actually stitched together from dozens of tiny independent components.
Right, very common these days.
This specific test site requested 95 different resources. Under legacy HTTP 1.1 with Nginx, the framing overhead, just the metadata, the envelopes carrying the letters, accounted for 31% of the total bandwidth used.
Nearly a third of the data flying back and forth across the wire was just bureaucracy.
Right. But then they ran the same 95 resource site under EonFlow with x-gnosis, and that framing overhead dropped from 31% down to 0.03%.
0.03%. It is the complete annihilation of network overhead. It means 99.97% of the data you are downloading is actual usable content.
It's incredible. So x-gnosis is completely bilingual. It speaks standard, bloated tourist HTTP for regular browsers, but it has this ultra-efficient, secret native language for custom clients who are in the know.
Exactly.
But here is my question. If I am just a regular user, sitting in a coffee shop on my laptop, opening Safari, my browser still speaks HTTP 1.1. It doesn't know what EonFlow is. So do I, as a standard user, even see a benefit from x-gnosis being used on the back end? Or is this only for custom apps?
That is a vital question, and the sources address it directly. The answer is absolutely yes. Standard users see a massive benefit immediately. Even when the client browser is forcing the server to speak clunky legacy HTTP, the server-side scheduling efficiency is still fully in play.
Wait, how does that work if it's still sending the bloated headers?
Because x-gnosis handles that bloat differently. It receives the giant HTTP request, but internally it immediately translates it using leaner internal headers. It uses that amortized internal scheduling, like the middle-out projection caching we talked about.
Yeah.
It drastically reduces the actual CPU work the server has to do to process that legacy request. The result is that even over HTTP, x-gnosis requires fewer network round trips and faster assembly of the page compared to traditional Nginx.
Oh, I get it. So by parsing Nginx configs, it serves as an immediate, frictionless drop-in replacement that makes today's web faster.
Right.
But by dual-serving this EonFlow protocol, it is essentially acting as a Trojan horse for the next generation of the internet. It is sneaking a mathematically perfect protocol onto the web while wearing a familiar Nginx mask.
That is the perfect way to characterize it. It solved today's problems while silently laying the tracks for tomorrow's optimal web.
But wait, routing traffic and parsing config files is really only half the battle, and Nginx is just the traffic cop directing the cars. What about the actual destinations, the applications themselves?
Right, back-end code.
Yeah. If you are a software company, your developers have spent decades writing your actual business logic in entirely different programming languages. You have Python apps, Java enterprise backends, Ruby on Rails sites, Node.js services. Does x-gnosis force you to rewrite your actual application code into its mathematical language?
No, it does not. And this is where the system shifts from being a great networking tool to being a holistic infrastructure platform. X-gnosis solves the application problem using something called the Gnosis Ditto Compatibility ABI.
ABI, Application Binary Interface. How does Ditto work?
The Ditto ABI allows x-gnosis to run legacy application code natively in place. You do not have to rewrite your application.
Not a single line.
Nope. The framework supports a massive, sweeping range of legacy languages and architectures.
Yeah, the list in the sources is exhaustive. If you wrote an app in JavaScript or TypeScript using frameworks like Koa or Fastify, or if you use Go with Gin, Fiber, or Echo, or Python with Flask or FastAPI, or Ruby with Sinatra, or even enterprise Java with Spring.
It covers, essentially, the entire modern enterprise web stack. Now, to understand how it runs these, we have to talk about middleware hooking. Let's take a classic Express application in Node.js. Express operates on a very specific paradigm known as the request next model.
Request, response, and next.
Right. A request comes in, it hits a middleware function maybe to check if the user is logged in. If they are, it calls next to pass the request to the actual page logic, which eventually formulates a response.
Pretty standard web flow.
x-gnosis physically intercepts those middleware registrations at the runtime level. It extracts your application's route table, the map of all your endpoints, like /users or /products, and it maps that logic directly into its perfect mathematical.g topology.
I am going to be totally honest with you. As someone who has watched development teams spend 6 months trying to migrate a simple database, this sounds incredibly risky.
It sounds like a recipe for disaster, you
Sure.
think?
Yeah. You were talking about taking a legacy Python app and a heavy Java Spring application, ripping out their core routing nervous systems, and plugging them directly into an alien mathematical supercomputer's mainframe. If you're a developer listening to this, your alarm bells are probably ringing. How does this not just instantly crash and burn in a nightmare of compatibility errors?
Your skepticism is entirely warranted. Migrations are historically the most painful part of software engineering. The strangler fig pattern, where you slowly replace an old app piece by piece, exists entirely because rip and replace migrations usually fail.
Right.
But the creators of x-gnosis state a very clear, defining invariant in their documentation that explains why Ditto works safely. The rule is backport semantic families, not framework brands.
Backport semantic families, not framework brands. Break that down for me. What is a semantic family?
Well, think about what all of these wildly different web frameworks actually do at their absolute core. Underneath the marketing, underneath the specific syntax of Python's Flask decorators or Java Spring annotations, they are all executed the exact same semantic sequence.
Which is what?
They take an incoming HTTP request,
Mm-hmm.
they route it based on the URL path, they execute some intermediate middleware logic like authentication, and they return an HTTP response. That fundamental sequence route, middleware, respond, is a semantic family.
Oh, so x-gnosis ignores the window dressing.
Exactly. x-gnosis does not care about the brand. It doesn't care if it's Spring or Flask. It looks at the underlying behavior and normalizes that behavior into its pure, mathematically verified topology.
Wow.
It looks at the Java app and effectively says, I don't care about your complex Java annotations.
Yeah.
I see that fundamentally you are just accepting a GET request at the /user's endpoint and returning a JSON list of names. My math can execute that semantic sequence perfectly.
And what happens if you throw something truly obscure at it? What if a company has a critical microservice written in a language that Ditto doesn't have a specific framework interceptor for? Does it just fail?
No,
Yeah.
they have engineered a robust fallback mechanism. If Ditto detects the language but doesn't recognize a specific branded framework, it routes the request into a standard script service lane.
What's that?
This lane supports nearly 20 different languages, including Rust, C++, PHP, Lua, Zig, and many more. It essentially executes the source file once per request using shared x-gnosis _ HTTP environment variables.
So it falls back to a very basic execution model.
Right. It grabs the standard output from your script and normalizes it back into a proper HTTP response. It acts as an incredibly resilient shell around almost any code you can throw at it.
Okay, so let's take stock of where we are. We have a mathematically perfect web server core. We have an Nginx Trojan horse to ingest legacy routing configurations. We have the Ditto ABI to absorb and optimize the world's existing application code.
A pretty complete package.
But code is just instructions. Where does the actual data live? Because as I read through these sources, it becomes clear that x-gnosis isn't just trying to build a better server. It is actively trying to redefine the concept of a file system entirely.
That is a very accurate assessment. The traditional concept of a file system. Think of the C drive on your Windows machine, or the root directory on a Linux server sitting in a rack somewhere, is inherently localized and passive.
It's just a folder holding stuff.
Exactly. X-gnosis introduces a concept called Rhizome. Rhizome supports a D1-backed VFS, or virtual file system.
Let's clarify those terms for the listener. D1 is Cloudflare's serverless SQL database that runs on their edge network, right?
Church.
And a VFS, virtual file system, means the software interacts with it as if it's a local folder, even if the files are physically distributed across the globe.
Spot on. This D1-backed virtual file system sits in front of the local physical file system. So the server checks the global lightning-fast edge database first. But the true innovation isn't just where the files are stored. It is what the files inherently are.
What do you mean?
Well, x-gnosis exposes native endpoints specifically labeled /.eon/object/rhizome. And according to the architectural docs, a file in rhizome is not just a dumb JSON document or a passive block of text. It is an Eon object envelope.
An envelope. What exactly is inside this envelope?
The raw data is inside, of course. But crucially, the envelope also contains the object's identity. Its cryptographic witness, meaning the proof of who created or modified it, its storage scope, and its replication policy, which dictates how it should be copied across the global network.
So it's bundled together.
Yes, all of this metadata travels bound to the object itself.
I love this concept. If you think about a traditional file on your computer, it's just dumb data sitting in a folder. It has no agency, it just waits to be opened. But under this rhizome architecture, an object is more like a high-level diplomat traveling internationally.
A diplomat. Okay, I see where you're going.
The diplomat carries a briefcase with the actual message inside, sure. But the diplomat also carries their own passport for identity, their own security clearance badges, and a strict list of instructions dictating exactly how the host country is allowed to handle them.
That is a phenomenal way to visualize it. The infrastructure itself understands the context and the rules of the data, not just the raw bytes. When the server shell queries an object, x-gnosis returns that fully normalized envelope, regardless of whether the object inside is meant to be opened as a static text document, launched as an interactive application, run as an autonomous AI agent, or streamed as live video.
It's completely context-aware.
The server inherently knows how to treat the object based on the envelope.
And the server handles the security checks for this traveling diplomat as well, doesn't it? The sources outline a platform auth mechanism called UCAN.
Yes, UCAN stands for User-Controlled Authorization Networks. It is a massive leap forward in decentralized security. In a traditional system, every time a user requests a secure file, the server has to pause, connect to a central database, look up the user's ID, check their permissions, and then wait for the database to reply. That takes time.
Right. It's like a bouncer at a club having to call the manager on a walkie-talkie for every single person in line to ask if they are on the VIP list.
Exactly. It slows everything down. UCAN eliminates the walkie-talkie. It uses cryptographically signed bearer tokens.
So the token proves the identity by itself.
Yes. x-gnosis can resolve and verify a UCAN token right at the ingress point, the exact microsecond the request hits the edge of the server. It mathematically derives a zero-trust Aeon PID auth context, stamps the internal headers, and sends it through.
Without calling the central database.
Right. Downstream systems can implicitly trust that validation because the cryptography guarantees it. The server only have to perform deeper, slow database capability checks if it is strictly necessary for a highly sensitive operation. Pushing that security to the edge of the network makes access control blazingly fast.
And speaking of pushing things to the edge, there's a fascinating note in the architecture docs about a first-class Tori Edge runtime lane. Now, if developers are listening, they probably know Tori as a framework used for building standalone desktop applications, kind of like Electron. What on earth is a desktop application framework doing baked into a web server?
This is where x-gnosis blurs the line between local development and global deployment. x-gnosis has the ability to take a certified Tori-derived edge artifact, reconstruct it deterministically from a manifest file, hydrate it into a local spool, and surface it as a resumed live guest application.
Hydrate it. That is such an evocative technical term, meaning it can take a complex application that is essentially frozen in a dormant state in a database at the edge of the network, thaw it out in milliseconds, and run it live on the server instantly as if it were a native process.
Exactly. It seamlessly blends local workflow with global compute. A developer could be working on their local laptop, pointing their tools directly to a Unix socket Forge VFS bridge to write code and instantly invalidate caches.
And that scales instantly.
Yes, and that exact identical setup runs globally, distributed across Cloudflare's massive edge network. The historical friction between it works on my laptop and it broke on the global internet completely vanishes.
Okay, I think we need to take a step back and look at the physical reality of what we are discussing. We are talking about a server that is thawing out frozen edge applications, translating Python and Java code on the fly into mathematical models, cryptographically verifying traveling diplomats at the ingress point, and executing simultaneous three-way races to fetch files.
It is a lot of heavy lifting.
To manage all of this complex, heavy orchestration at the mathematically optimal limits we discussed earlier, the underlying physical hardware integration has to be absolutely flawless. You can't run a finely tuned Formula One engine and bolt it onto a rusty bicycle chassis. Let's look at the literal physical engine block of x-gnosis.
The physical engine block is a custom transport layer called Gnosis Uring. It is written entirely in native Rust.
Rust being the programming language famous for its obsession with memory safety and zero-cost abstractions?
Yes, it is the absolute perfect language for this, and Gnosis Uring relies heavily on a Linux kernel feature called iring.
I know iring has been making massive waves in systems programming recently. Can you explain to the audience why it is so critical for performance?
Well, to understand IRing, you have to understand the tax that the Linux operating system usually charges software. Normally, when a web server wants to read a file from the hard drive or send data over the network, it has to execute a system call.
A system call. Okay.
The application has to pause its own work in user space, ask the Linux kernel in kernel space to do the physical hardware interaction, wait for the kernel to finish, and then switch back.
So it's constantly pausing.
Constantly. This constant context switching is incredibly expensive in terms of CPU cycles. It is like driving on a highway and having to stop at a toll booth every 100 yards.
You just lose all your momentum.
Exactly. IRing bypasses the toll booths entirely. It creates shared ring buffers, circles of memory that both the application and the kernel can access simultaneously.
Oh, wow. So they don't have to wait for each other.
Right. The web server can just drop a list of requests into the ring buffer, and the kernel picks them up and processes them asynchronously without the application ever having to pause or execute a traditional system call. It is pure, non-blocking asynchronous I/O.
But the sources highlight a fascinating benchmark regarding hardware limitations. What happens when x-gnosis is run on a system that doesn't have IRing? They tested it on macOS, which doesn't support it, right?
Yes, they force the server onto a macOS blocking fallback path. This is x-gnosis running in a degraded fallback state, completely stripped of its primary high-speed hardware advantage.
And what were the throughput numbers on that degraded fallback state? Because this is the real test.
Even on a macOS blocking fallback path serving non-pipeline plaintext, x-gnosis still hit 153.8 thousand requests per second.
153,800 requests per second while running in its degraded state.
Yes. The developers note this is a massive leap from even prior optimized Linux snapshots. It achieves this through what they call a whip-snap multi-worker architecture.
Whip-snap architecture.
Right. It natively handles fragmented HTTP pipelining, meaning it can reassemble broken data streams flawlessly, and it utilizes a bounded same-request collapse table.
That sounds dense. What does that architecture physically achieve at the hardware level?
It enables native zero-copy responses. In a standard, unoptimized server, sending a file is highly inefficient. The server reads the file from the hard drive, copies that data into the kernel's memory, copies it again into the application's memory buffer to format it.
And then copies it a third time back down to the network socket to send it out, right?
Exactly. 3 separate copies. X-gnosis uses zero-copy architecture. The data is orchestrated to move straight from the storage drive directly to the network interface card.
It just skips the middleman.
It completely bypasses the application memory and kernel bloat entirely. That physical hardware optimization is what allows the theoretical Pareto optimal math from our first section to actually exist in physical reality.
But the creators didn't just stop at zero-copy efficiency. Hidden deep in these hardware specifications is perhaps my favorite detail in the entire source document, a feature that feels completely out of place at first glance.
I think I know what you're talking about.
The documentation casually mentions that the x-gnosis package includes a native HFT parallel simulator.
Yes, HFT, high-frequency trading.
Right, high-frequency trading. The complex algorithms used by Wall Street quantitative analysts to buy and sell stocks in fractions of a microsecond based on market fluctuations. The sources state they built an HFT simulator called Gnosis Rayon via a BUN FFI bridge, and it evaluates over 32 million tick configurations in about 1.5 seconds.
From a raw computational standpoint, it is an astonishing piece of software engineering.
But like, why is it there? I am genuinely baffled. Did they just casually throw a massive Wall Street high-frequency trading simulator into an open-source web server package? Is this just a massive engineering flex?
It really is.
I'm trying to think of an analogy. It's like buying a sensible luxury family sedan, opening the glove box, and discovering the manufacturer installed a live Formula One telemetry and aerodynamics dashboard, just to prove to you how much spare processing power the onboard computer has.
That is pretty much exactly what it is. It is absolutely a flex. There's no denying the swagger involved here, but it is a very purposeful, strategic flex.
Okay, I'll bite. How does simulating the stock market prove anything about serving web pages?
Because it proves the absolute viability of the underlying compute substrate. Let's unpack how it runs. Gnosis Rayon relies on a BUN FFI bridge. FFI stands for Foreign Function Interface.
Okay.
It allows the JavaScript runtime, BUN, to seamlessly call functions written in the Rust Rayon library, which is specifically designed for data parallelism and massive multi-threading execution.
So it bridges the two languages perfectly.
Right. By demonstrating that the server's compute layer can handle massive parametric alpha discovery, which is essentially running millions of complex concurrent mathematical market equations simultaneously without crashing, they are proving the server's raw compute power for hosting edge guests.
Ah, they're saying, look, if our web engine can handle the most computationally punishing, latency-sensitive task in the global financial sector in a second and a half, it can definitely handle running your API routing logic.
Exactly. It validates that the mathematically derived topology doesn't just work for pushing static images. It scales perfectly for executing massive parallel computational workloads at the edge.
We can simulate the global economy in the time it takes you to blink. I think we can manage to load your user's profile picture. That is incredible. Okay, so we've covered the theoretical math, the legacy compatibilities, the zero-copy hardware optimizations, and the massive computational flexes.
You've covered a lot of ground.
But we don't live in a theoretical world. We live in the real world, where servers have to compete. How does x-gnosis perform in direct head-to-head combat against the actual servers running the internet right now? The sources gave us the receipts for a major shoot-off.
They did. They set up a rigorous shoot-off against the heavyweights of the modern web. Nginx, which serves as the baseline for HTTP 1.1, Caddy, which is widely praised for its modern HTTP 2 implementation, and H2O, which is a highly optimized HTTP 3 server.
The big three. Let's look at how they handled compressed assets, because this is where the numbers get truly staggering. They ran a local gzip control test against Nginx. They were serving standard compressed assets, CSS-style sheets and JavaScript files, the building blocks of every website. How did Nginx perform?
When serving the compressed CSS, Nginx managed about 2,136 requests per second, which for a local test is a very respectable standard number that most sysadmins would be perfectly happy with.
It's the standard, right? And what happened when they put x-gnosis in the exact same environment, serving the exact same CSS file?
Under the exact same conditions, x-gnosis hit roughly 42,700 requests per second.
That is a 20-fold increase. 42,700 compared to 2,100. As an outside observer, I have to ask, how is that physically possible when the underlying hardware and the files being served are identical?
To understand that gap, we have to look at how the servers position themselves in the networking stack. The architectural documents explain that x-gnosis heavily optimizes Layer 7, the application server architecture, and Layer 8, their custom Lambda transport pipeline.
Okay, the networking layers.
Right, because x-gnosis utilizes a mechanism they call per-chunk codec racing. It pipelines the data compression perfectly in sync with the physical I/O disk reads.
Let's define codec racing. How does it differ from what Nginx does?
In a traditional setup, compression is often a discrete step. The server reads the file, passes it to a gzip algorithm, waits for it to compress, and then sends it out.
One step at a time.
Exactly. X-gnosis streams the data and actively races the encoding processes concurrently. It pipelines the compression simultaneously with input and output operations.
So it's multitasking at the lowest level.
Yes. This methodology strictly dominates traditional legacy methods like Nginx's sendFile directive for compressible content. It is literally doing the complex compression math while the file is already flying out the door. That is why it annihilates Nginx on compressed asset delivery.
And we see this efficiency bear out again in the complex microfrontend site test. This was the site we mentioned earlier that required 95 separate resource files to load a single page.
Correct. On standard HTTP, Nginx required 16 distinct network round trips to fetch all the files, suffering from a 31% framing overhead.
And x-gnosis?
X-gnosis served the exact same site in only 11 round trips, dropping the framing overhead to 19.4% even while constrained to legacy HTTP.
And as we established earlier, if the client is capable of speaking the native Eon flow protocol, that overhead plummets to essentially zero with only a single round trip.
Exactly.
But as I read through these benchmarks, the most revealing and profound test in the sources isn't the one where x-gnosis wins by a massive 20-fold landslide. It's the test where it actually ties.
Ah, yes, the hostile network condition tests.
The engineers took all of these servers, x-gnosis, Nginx, Caddy, and forced them to operate over simulated hostile networks. They tested them on degraded cellular network conditions, lossy networks where data packets randomly disappear, and networks experiencing severe dribble or intentional bandwidth throttling.
And the results of that test are fascinating.
Under those terrible hostile conditions, all the servers converged to nearly the exact same transport ceiling. They all slowed down to a crawl together.
X-gnosis lost its massive lead.
Right.
So when network conditions are perfect, x-gnosis is essentially teleporting data while the legacy servers are stuck in traffic. But when the network goes hostile, like a user trying to load a website on a weak cellular connection in a crowded football stadium, everyone gets stuck in the exact same mud. Nginx and x-gnosis perform roughly the same.
Which is exactly what should happen. And it proves the foundational thesis of the entire x-gnosis project perfectly.
Oh wait, I need you to explain that. How does getting stuck in the mud, losing your speed advantage, prove that your server is mathematically optimal?
Because you have to analyze what causes the baseline gap versus the impaired gap. The 20-fold increase in speed under perfect conditions is a server path difference.
Okay.
It proves that under normal circumstances, legacy servers like Nginx are the actual bottleneck. Nginx's internal architecture limits the speed long before the physical network wire does.
Ah, the server itself is the problem.
Right. But when the numbers converge perfectly under hostile conditions, it proves that the impaired gap is purely a wire limit constraint.
Niners.
It means x-gnosis has essentially solved the server-side computational equation so completely and so optimally that the server is no longer the limiting factor. The only remaining limit in modern web hosting is the physical laws of thermodynamics governing the copper or fiber optic wire connecting the user's house to the internet. The software is no longer the problem.
Wow. Let's just sit with the magnitude of that for a second. We started this deep dive talking about how modern software engineering is historically a chaotic game of empirical guesses. You build something, you hit it with a simulated hammer, and if it doesn't fall over, you ship it to production and call it a day.
That's how we've always done it.
But over the course of this exploration, we've walked through an incredible, rigorous journey of replacing that guesswork with certainty.
We started with a foundational stack of abstract mathematical proofs, 14 mechanized theorems rigorously verified in Lean 4 without a single sorry or logical gap.
We saw how the creators translated that pure math into a physical server topology that constantly races internal processes, instantly venting the losers to maintain perfect, Pareto optimal resource equilibrium.
We explored how x-gnosis acts as an elegant Trojan horse, natively parsing standard Nginx configurations to fix today's web, while secretly serving the ultra-efficient, headerless Eon Flow protocol for tomorrow's web.
We dug into the Ditto ABI, proving that you don't have to rewrite the internet to save it. It can intercept the semantic brain of your legacy code, whether it's Python Flask or Node Express, and run it natively at mathematically optimal speeds.
We examined Rhizome and the D1 virtual file system, redefining files not as static data, but as traveling diplomats carrying their own UCAN security contexts and replication rules, backed by global edge databases.
We laughed at the absolute hardware swagger of utilizing an iron zero-copy substrate to casually run a multi-threaded, high-frequency trading simulator just to prove the parallel processing engine was bulletproof.
And finally, we examined the receipts, the head-to-head combat where x-gnosis dominated the industry standards, proving conclusively that it has shifted the fundamental bottleneck of the internet away from the software and onto the physical wire.
It is a staggering, monumental achievement in computer science. And as a listener, I really want you to think about how this applies to your world. Think about how much of the software you rely on every single day. The banking applications that hold your money, the communication tools you use for work, the medical databases, managing your health records. How much of that critical infrastructure is built on those old empirical guesses, on that fragile, good enough mentality?
And imagine what might happen if this zero-deficit, mathematically proven mindset was applied to the systems you interact with, or the systems you build. What long-held assumptions are you making in your own work that are just waiting to be rigorously, provably solved rather than just optimized?
It leaves us with a massive, provocative question to mull over as we wrap up today. If x-gnosis has successfully proven that the foundational plumbing of the internet, the web server itself, can be mathematically solved and perfected, what else is waiting? What other massive, chaotic, unpredictable systems in our daily digital infrastructure are currently just surviving on good enough benchmarks, waiting for their theorem? Are we entering a new era where our most important life-critical software isn't just written and tested, but logically derived from the immutable laws of mathematics?
It fundamentally changes how you look at the entire digital world. The horizon of what is possible just expanded.
It really does. Because maybe, just maybe, that X-ray machine for software precision isn't broken after all. Maybe we just finally figured out how to plug it in. Thank you so much for joining us on this deep dive. Stay curious, keep exploring, and we will catch you next time.